Today, we will learn grouped frequency distribution. Your school must have a fitness test every year. A fitness test was also taken at Adarsh Public School, in which the pulse rate of 100 children was thus obtained. The numbers collected for any information is called data. But it is not easy to get information from this data easily or draw any conclusions. Such data is called as raw data. To understand them, we can arrange them in ascending order or descending order. Pause the video and arrange them in ascending order. Is it easy? As the number of figures increases, it becomes difficult to organize them in any order. Another way of arranging these is that we create a table and write the pulse rate in first column and show how many times the pulse rate is repeated in the second column as tally marks and write the number of the tally marks in the third column. This number will tell us how many times the pulse rate is repeated in the data. The number of times an observation is repeated is called the frequency of that observation. For example, the pulse rate of 3 children is 61. We say that the frequency of 61 is 3. By arranging the data in such a way, we get the frequency distribution table. Since data groups are not created here, this is an ungrouped frequency distribution table. Since the data here are many and varied, the frequency distribution table will be longer. It will also be difficult to make such a table and get any information from it. In such a situation, we can make them smaller by forming groups of data. The smallest number in the given data is 61 and the largest number is 99. In this way, the range of data is from 61 to 99. So we will condense the data into groups in such a way that the numbers greater than or equal to 61 and less than or equal to 99 are included in them. Here we can make groups like 61 to 65, 66 to 70, 71 to 75, etc. We call each such group a class or class interval. The smallest number in a class interval is called the lower class limit of that class interval, and the largest number is called the upper class limit of that class interval. The difference between the upper class limit and lower class limit of a class is called class size or class width. Keep in mind that the size of each class interval is the same here. Now we will represent the data falling in these groups by tally marks. The first number is 74, which will be included in the class interval 71 to 75. The second number is 61, which will be included in the class interval 61 to 65. Similarly, we will represent all numbers as tally marks. By counting the tally marks, we will know how much data is included in each class interval. That means, what is the frequency of each class interval? This type of table in which the data is grouped or organized by grouping is called a grouped frequency distribution table. Now, we can get information from this table more easily, like the pulse rate of 25 children is between 71 to 75. We can also form groups of 60 to 65, 65 to 70, 70 to 75, etc. To organize the given data, let's organize the data into these groups. The first number is 74, which we will include in the class interval of 70 to 75. The second number is 61, which we will include in the class interval of 60 to 65. The third number is 65. Can you tell in which group we will include it? Think. Here we see that the number 65 can be included in these two groups, 60 to 65 and 65 to 70. But if it is included in both, then it will be counted twice, which is wrong. To avoid this, we follow convention. The common or overlapping observation between two intervals is considered in the higher class interval. In this way, we will include 65 in the 65 to 70 class interval. Similarly, we will group all the numbers. In this way, we will also get a grouped frequency distribution table here. Let's compare the first table with this table. Do you see any difference between the two? Think. Let us tell. None of the two classes in this table have overlapping lower class limit or an upper class limit. That means that classes are not overlapping. Such classification or distribution of data when the class is non-overlapping. This is called discontinuous frequency distribution. In this way, it is a discontinuous frequency distribution table. If we talk about this table, then there is overlapping of the classes in it. That is, the classes are overlapping. Such a distribution of data is called continuous frequency distribution. This gives us a continuous frequency distribution table. Today we learn grouped frequency distribution. In the next video, we will solve some interesting examples related to them. Today we will see examples related to grouped frequency distribution. Example: the height of children in a class was measured. The frequency distribution table shown below shows the data related to it. Convert the shown table into a continuous grouped frequency distribution table. The table shown below shows the discontinuous frequency distribution because the class intervals here are non-overlapping. That means there are gaps between upper and lower limits of two consecutive class intervals. Suppose the height of a child is 129.5 centimeter, then in which class interval will it be included in the table? Think. Let us tell. Since 129.5, this number is greater than 129, it cannot be included in the class interval 120 to 129. Similarly, 129.5, this number is smaller than 130. So, it cannot be included in the class interval 130 to 139. Thus, this number cannot be included in any class interval. In such a situation, it is necessary for us to convert the discontinuous frequency distribution into a continuous frequency distribution table. So, let's start. To obtain a continuous frequency distribution, we must divide the class intervals. This will make the upper and lower limits of consecutive intervals equal. For this, we will subtract the upper limit of one class from the lower limit of the next class in consecutive order and divide the result by 2. Like we will subtract the upper class limit 129, which falls on 120 to 129 from the lower class limit 130 of the next class, 130 to 139, and divide the result by 2. This will give us the result as 0.5. Now we will subtract 0.5 from the lower limit of each class, such as 120 minus 0.5 is equal to 119.5. Similarly, we will add 0.5 to the upper limit of each class, like 129 plus 0.5 is equal to 129.5. In this way, we will create a new class interval 119.5 to 129.5. Now, you pause the video and similarly, in this way, find all the class intervals. You will get the class intervals as follows. Can you tell whether these class intervals are continuous or discontinuous? These are absolutely continuous class intervals. Now we can organize these groups in this way. Now, this table is a continuous frequency distribution table. Now, can you tell in which class interval 129.5 will be included? Think. Absolutely right. 129.5 is overlapping between the class intervals 119.5 to 129.5 and 129.5 to 139.5. And we include overlapping observations in higher class intervals. So the number 129.5 will be included in the class intervals 129.5 to 139.5. Today, we saw example of a grouped frequency distribution. In the next video, we will see some more examples related to this. Today, we will see some more examples related to grouped frequency distribution. Before looking at any example, let's understand what a class mark is. The midpoint of any class is called the class mark of that class. The midpoint of a class interval, that means the class mark, is obtained by dividing the sum of the lower class limit and the upper class limit by 2. For example, the midpoint of a class interval 10 to 20 is 15. That means the class mark of a class interval 10 to 20 is 15. Similarly, can you tell what will be the class mark of class interval 150 to 190? Think. Absolutely right. Its class mark is 170. Let us now see some examples related to this. Example: if the class mark of a class is 45 and the upper class limit is 65, find the class interval. Here the class mark is 45 and the upper class limit is 65. Let x be the lower class limit. Now we can say that the class mark 45 equal to the sum of lower class limit x and upper class limit 65 divided by 2. By simplifying it, we will get the lower class limit x is equal to 25. In this way, the class interval is 25 to 65. Example: the table shown below represents the midpoint of the class intervals. From this information, make a continuous frequency distribution table. The midpoints of the class intervals are shown in the given table. To make a continuous frequency distribution table, we need to find the class interval. Here, we are not given the lower class limit or upper class limit of any class interval. Can you tell how we would find the class interval in this case? Think. Let us tell. Suppose the midpoint of a class is M and the class size is H. You must remember that the difference in the upper class limit and lower class limit of the class interval is called its class size. Since the midpoint is between the middle of class intervals, so difference between any two consecutive midpoints will have the same difference as the difference between a lower and upper class limit of a class interval. In this way, we will find the class size h by the difference of consecutive midpoints, which is 20 minus 10 is equal to 10. If we reduce this difference to the half of class size, we will find the difference between the midpoint and the lower class limit or the midpoint and the upper class limit. H divided by 2 equal to 10 divided by 2 equal to 5. If we subtract this difference from the midpoint, we will get the lower class limit 10 minus 5 equal to 5. Similarly, if we add this difference in the midpoint, then we get the upper class limit 10 plus 5 equal to 15. In this way, we get the first class interval 5 to 15. In the same way, we can get the lower class limit 15 of another class by subtracting 5 from the midpoint 20 and adding 5 to 20 to get the upper class limit 25 of the second class. So, the second class interval will be 15 to 25. Similarly, we can find all class intervals in this way. Now we can make continuous frequency distribution table in this way from the information given. So today we have seen some interesting examples related to grouped frequency distribution.
Today we will learn about bar graph. You must have seen the bar graph many times. Like here, this represents India's literacy rate in percentage. Looking at this, we can compare the literacy rate of given years. The elevations of various mountain peaks of the world are shown in this bar graph, so that we can compare them. Similarly, the result of the State Assembly election of State A is shown in this bar graph. Looking at this, we can compare the seats won by different parties. Let's understand this bar graph. In this bar graph, there is a horizontal line which we call the x-axis and the vertical line that we call the y-axis. Here, party is on the x-axis and the number of seats is on the y-axis. Simultaneously, the scale is also shown here, which tells us that 1 unit on the y-axis means 10 seats. Here, vertical lines of uniform width are drawn at equal distances. These are called bars. All the bars in the bar graph are of equal width and have the same distance. In the bar graph, the data is represented as the length of the bar. Thus, the graphical method of representing the data, in which data is represented by horizontal or vertical bars of equal width at the same distance, is called bar graph. Let us now know how to read a bar graph. Here, we see that the length of bar made for party Q represents 56 seats. In this way, we can say that in State Assembly elections, party Q won 56 seats. Similarly, can you tell how many seats the party R has won? Think. Absolutely right. For the length of bar made for party R, we know that party R has won a total 54 seats. The comparison of data becomes easy with the help of bar graph, as the maximum length bar has been drawn for party P. Here we can say that party P has won the most seats. Can you tell how many more seats did party Q win than party S? Think. Absolutely right. We see that party Q has won 56 seats while party S has won 44 seats. Therefore, party Q has won 56 minus 44 is equal to 12 seats more than party S. Here we have shown a vertical bar graph. We can also represent it horizontally, wherein we show the parties on the y-axis and the number of seats on the x-axis. We call this bar graph the horizontal bar graph. Now, let us know how to draw a bar graph with the help of an example. The table shown here shows the lengths of some of the major rivers in India. Let's represent these data as a bar graph. Draw two mutually perpendicular lines on the paper. The horizontal line is the x-axis and the vertical line is the y-axis. Now we will show the names of the rivers on the x-axis and the length of the river on the y-axis. Now we will choose a convenient scale. Can you tell which convenient scale shall be taken to show the length of the river? Think. Let me tell you, the longest length here is 2900 kilometers and the shortest length is 800 kilometers. In order to represent both correctly, we can take a convenient scale in this way. We can take 1 unit is equal to 500 kilometers. The number will show numbers on the y-axis according to the scale. Now, we will draw the bar according to the length of each river. For example, here we have drawn a bar denoting the length of Narmada river at 1300 kilometers. Similarly, we will represent the lengths of all rivers as bars. Remember that the bars should have the same width and should be equally spaced. So today we have learned the bar graph. In the next video, we will see some examples of these. Today we will see some examples related to bar graph. In a school, measurements of children's shoes were taken for the annual ceremony. These are as follows. Represent the given information in a bar graph. Let us assume 1 unit is equal to 20 students and draw a bar graph based on the information with a given scale. On the paper, draw the horizontal line x-axis and the vertical line y-axis. We will show the shoe measurement on the x-axis. Similarly, we will show the number of students on the y-axis by taking scale as 1 unit is equal to 20 students. Since the maximum value is 108, we will end the number of students on the y-axis at 120. Now, we will draw the bar in vertical for each measurement of shoes whose length represents the number of students. In this way, we will draw the bars for all measurements of shoes. Thus, we have drawn the bar graph for the given information. Next example, the bar graph shown depicts India's performance in the Asian Games. Read the bar graph and answer the following questions. In which year India received maximum medals? The longest bar in the bar graph has been drawn for 2018. Since the number of medals is denoted by length of the bar, we can say that India received the most medals in the year 2018. How many medals did India receive in 2010? From the length of the bar drawn for the year 2010, we know that in 2010, India got total of 65 medals. How many more medals India got in 2006 as compared to 2018? In 2006, India got 53 medals and in 2018, it got 69 medals. There is a difference of 69 minus 53 is equal to 16 medals in the number of medals received in the both years. Calculate the decline in the number of medals from the year 2010 to 2014. India received 65 medals in 2010, while in 2014, 57 medals were received. In this way, from the year 2010 to 2014, the number of medals has fallen from 65 minus 57 is equal to 8 medals. Next example. In 2017, a survey was conducted in India to know the number of newspaper readers. The details of some highly read newspapers are shown in the bar graph. Read this number and find out the answer to the following questions by yourself. Which newspaper has the most readers? How many people read the Hindustan newspapers? How many people read the Lokmat newspaper? What is the difference between the number of readers of Dainik Jagran and Lokmat? So today we have seen some examples related to bar graph. In the next video, we will see some mistakes related to them. Today we will learn histogram of uniform width. In a school, a computer teacher organized a competition to understand the students' typing speed, in which the students were given 5 minutes and asked to type a text of English. Following information was collected about how many words students type in a given time. Due to large number of observations, they thought it would be appropriate to organize them into a grouped frequency distribution table as follows. Can you tell what kind of distribution it is? Think. Absolutely right. Since the class intervals are continuous, it is a continuous frequency distribution. If we represent these figures in a pictorial form, we can get information more easily. Let's represent these figures in a pictorial form. Can you tell if a bar graph would be appropriate to represent these data or a histogram? Think. Let me tell you. Histograms are an appropriate means to represent continuous class intervals. Therefore, we will represent these figures as histograms. First, draw the x-axis and y-axis on graph. On the x-axis, we will take the number of words typed in 5 minutes and the number of students on the y-axis. Here, class width, that is, class width of all class interval is same, which is 20 words. Therefore, we will take the scale 1 unit is equal to 20 words on the x-axis. Class intervals begin at 60 and end at 180. Since the first square interval is starting from 60 here, we do not have to show numbers from 0 to 60 on the x-axis. To show that we are not taking the numbers from 0 to 60, we will draw a king symbol on the x-axis in this way. Thus, keeping in mind the scale on the x-axis, we will show numbers from 60 to 180. To show the number of students, we also have to take the appropriate scale on the y-axis. Here, a suitable scale would be 1, so that we can properly represent the smallest number 1 and the largest number 30. We can take this scale for the y-axis by 1 unit is equal to 5 students. Since the numbers 30, 15 and 10 are multiples of 5, it would be easy to represent them. Similarly, we can do 1 unit is equal to 5 students. Taking this scale and divide it into 5 equal parts of the unit, which will help us to represent numbers such as 1, 4 and 22. In this way, with the help of this scale, 1 unit is equal to 5 students, we will properly represent other numbers along with smallest and largest numbers. By choosing the scale, we will show the numbers on the y-axis. Now, we will represent the frequencies of class interval with rectangles. The frequency of class intervals 60 to 80 is 30. So, we will draw a rectangle for this class interval in such a way that the length will represent 30 students. Similarly, we will also draw rectangles for class intervals 80 to 100. Similarly, we will draw rectangles for all class intervals. The area of rectangle to be drawn for a class interval in a histogram is proportional to the frequency of that class interval. But here we have kept the frequency proportional to the length. Is it fair? Think. Let me tell you. We know that the area of a rectangle is length multiplied by width. Here, width of each class interval is the same. So, the width of rectangles to be drawn for them will also be same. If the width of rectangle is kept the same, then its area is proportional to its length. In this way, width of each class interval is the same. Then, the length of the rectangle can be taken in proportion to the frequency of the square intervals. This will also make the area of the rectangle proportional to the frequency of that class interval. In this way, we will get a histogram. Here, the data is classified as continuous frequency distribution. Since the histogram is used to represent a continuous frequency distribution, it does not contain distances or spaces between rectangles. As you can see in this histogram, there is no spaces between the rectangles. Various information can be obtained by looking at this histogram. The maximum number of children who can type 60 to 80 words in 5 minutes. We can see that only one student types 160 to 180 words in 5 minutes. When the class intervals have the same width, we get the histogram of uniform width. If the width of the class interval is not the same, then we get an histogram of varying width, which we will discuss in the next video. So today we learned about histogram of uniform width. In the next video, we will discuss about histogram of varying width. Today we will learn about histogram of varying width. In the previous video, we learned about the histogram of uniform width, in which we represent the number of words the students typed in 5 minutes as histogram of same width. Suppose a student classified these data in this way. Is the table the same as the one made in the previous video? No. Here we see that the class width of first class interval is 100 minus 60 is equal to 40. The class width of the second class interval is 120 minus 100 is equal to 20. And the class width of the third class interval is 180 minus 120 is equal to 60. Thus, the class width of the class intervals are different in this frequency distribution table. In order to represent these figures, the student drew the histogram in such a way that the length of rectangles to be drawn for class intervals was proportional to frequency. Did he draw the correct histogram? Think. No, this is an incorrect histogram. Let's understand the reason for this. We know that the area of a rectangle in a histogram is proportional to the frequency it represents. According to this statement, the area of each rectangle here should be proportional to the frequency. Since the frequencies of the class interval 100 to 120 and the class interval 120 to 180 are the same, the area of rectangles representing them should also be same, but the area of both appears different here. We can also understand it mathematically. Here we see that the rectangle representing the frequency 15 of the class interval 100 to 120 is 1.5 units in length and 1 unit of width. Thus, the area of this rectangle is length multiplied by width is equal to 1.5 square units. Similarly, the rectangle denoting the frequency 15 of the class interval 120 to 180 is 1.5 units in length and 3 units of width. Thus, the area of this rectangle is equal to 4.5 square unit. The ratio of the area of these rectangles is 1 by 3, but the ratio of frequency of both these class intervals is 1 by 1. Since the ratio of areas of rectangle is not proportional to their corresponding frequencies, the areas of rectangles are not proportional to the frequencies here. That is, these histograms show the wrong frequency of the corresponding class intervals. So this histogram is wrong. In the histogram, the area of rectangles must be proportional to frequency. The width of the rectangles depends on the class width of the class. The class widths here are different. Therefore, the width of the rectangles will also vary. If we want the area of rectangles to be proportional to the frequency, we must change the width or length of the rectangles. But the class width of each class interval is fixed. So, we cannot change the width of rectangles. So, we have to change the length of rectangles. Can you tell us how we will make this change? Think. Let us tell. For this, we will find the lowest class width of class intervals. Here, the class intervals are 100 to 120, class width 20 is the minimum class width. Now, we will multiply the result by the minimum class width by dividing the frequency of that class interval by the width of that class interval to find the length of rectangle of each class interval. For example, here the length of rectangle of interval 60 to 100 can be obtained as follows. Similarly, the lengths of the rectangle of other class intervals can be obtained in this way. Now, we will draw rectangles with a suitable scale for each class interval. Here, we have taken 1 unit is equal to 20 words on the x-axis and 1 unit is equal to 5 student scale on y-axis, from which we have obtained the histogram in this way. Now, you stop the video and find out whether the area of rectangle in this histogram is proportional to the frequencies or not. try it, you must know that now the area of rectangles is proportional to frequencies. Hopefully, you can now draw a histogram of varying width for a graded frequency distribution that has different widths of class interval. Today we have learned histograms of varying width. In the next video, we will see some examples of histogram. Today we will see some interesting examples related to histogram. Vinita had to know how many people are literate in her village. To find out, Vinita conducted a survey in the village. The information obtained from the survey was presented by Vinita in the frequency distribution table shown below. Can you represent this information as a histogram? In the given table, the width of all class intervals is not the same. Here, we have to make suitable changes in the lengths so that the area of rectangles is proportional to the frequency of the class interval. For this, we will first find the width of each class interval and choose the lowest class width. That is, here we will choose 10. Now, we will change the lengths of the rectangles in such a way that class width is proportional to 10. For this, we will divide the frequency of each class interval by its class width and multiply it by the minimum class width of 10. Thus, the length of the rectangle for the age group 10 to 20 will be 360 divided by 10 multiplied by 10 is equal to 360. Since the class width of the class interval 10 to 20 is already 10, therefore, there was no change in the length of its rectangle. Similarly, we will find the length of rectangles for all age group. Now, we will show the age groups on the x-axis and the number of literate people on the y-axis. For this, we will take 1 unit is equal to 10 years on the x-axis and 1 unit is equal to 40 persons on the y-axis. Since we are starting with 10 on the x-axis, we will thus make a kink symbol indicating that we are not showing numbers from 0 to 10. Now, we will draw the rectangle by keeping the width of the rectangle 10 and the length of the rectangle 360 for the age group 10 to 20. Similarly, we will draw the rectangle by taking suitable width and length for all age groups. In this way, we will complete the histogram. Thus, we have represented the information given as a histogram. Next example, Shruti is a reporter. To publish the news in the newspaper, Shruti studied the change in the price of 14.2 kg of liquefied petroleum gas, that is LPG, from the year 2006 to 2012. The information received was thus represented as a histogram and printed in the newspaper. Now, read this histogram and answer the questions below. The histogram shown here shows the change in the price of LPG over different years, in which the x-axis represent years and y-axis represent price of LPG per 14.2 kg. Here, the width of each class interval is the same, that is 1 year, and the scale of y-axis in 1 unit is equal to 100 rupees. Look at the histogram and find out for how many years the price of liquefied petroleum gas, that is LPG, is less than 500 rupees. Here, we see that price of liquefied petroleum gas is less than 500 rupees in the year intervals 2006 to 2007, 2007 to 2008, 2008 to 2009. Here, the width of each class is 1 year. Therefore, we can say that the price of LPG has been less than 500 rupees for 3 years. Can you tell what is the percentage increase in LPG price in the year 2008 as compared to year 2007? Here, the price of LPG in 2008 is 420 and in 2007 the price of LPG is 340. In this way, the price of LPG increased from rupees 420 minus rupees 340 is equal to rupees 80 from the year 2007 to 2008. This increase has been made at 340 rupees, so we will consider 340 as the base. In this way, the price of LPG has increased by 23.53%. Look at the histogram and find out how many years price of LPG ranged from 500 rupees to 800 rupees. In the year 2009-2010, in the year 2010-2011, class intervals, the price of LPG is between 500 and 800. So, we can say that in 2 years, the price of LPG ranged from 500 rupees to 800 rupees. Now, pause the video and try to make a histogram with this information. Today, we have seen some interesting examples related to histogram. In the next video, we will see some misconceptions related to them. Today we will see misconceptions related to histogram. Some students think that a bar graph and a histogram are the same. If they are asked to represent some information in a histogram, they make a bar graph. It is a misconception to think that bar graphs and histograms are same. Let's understand this. The data shown here in this table show the number of readers of different age groups visiting the library of Rahul's village in March. Rohan represented this information as a bar graph and Sohan represented this information as a histogram. Can you find the difference between two by looking at them? Think. Let me tell you, the same figures are represented differently in bar graphs and histogram. Both types of representations are correct in their respective places, but differences can be seen between the two. For example, in a bar graph, the length of bars is proportional to the frequency of observation. That is, the frequency of observations is represented as the length of bars, where the area of rectangles in the histogram is proportional to the frequency of the class intervals. That is, the frequencies are represented as the area of rectangle and not the length of the rectangle. Similarly, the bars in the bar graphs are of the same width, while it is not necessary in the histogram. If the class intervals are of the same width, then the rectangles are the same width, but if the class intervals are not of the same width, then the rectangles are also not of the same width. Histograms are created for continuous group frequency distribution, so there is no gap between rectangles. Bar graphs are drawn to compare different categories, while histograms are drawn to understand the distribution of data. For example, in this bar graph, all three age groups are taken as one category. Readers of different age groups can be compared. Like here, most readers are between 20 to 40 years of age. If we look in the histogram, we find the distribution of the number of readers in the age of 10 to 40. Today we have seen the misconception related to histogram. Today we will learn about frequency polygon. In the previous video, we learned to represent classified data as a histogram. Like the histogram, frequency polygon is also a way of representing classified data graphically. In this video, we will look at two ways to draw a frequency polygon, using a histogram to draw a frequency polygon and frequency polygon without a histogram. Let us learn to draw a frequency polygons with the help of histogram. Suppose the height of students of class 9 in a school are presented in this frequency distribution table. This distribution is a continuous frequency distribution because there is overlapping of class intervals. From the frequency distribution table, we can draw a histogram like this. Pause the video and think about it. Let's go ahead. To make a frequency polygon, first we need to find the midpoint of upper side of each rectangle. Midpoint of class interval 120 to 130 will be 125. Therefore, we will go to the upper side of the rectangle drawn on the class interval 120 to 130 and mark the middle point, followed by the vertical line representing 125 on the x-axis. 125 is the midpoint of class interval 120 to 130. We also call it a class mark. Let P be the middle point obtained. Here, the coordinate of point P are 125 and 5. Similarly, we will find the midpoint of the upper sides of all the rectangles. We assume that the class interval before 120 to 130 is a hypothetical class interval of 110 to 120 with a frequency of 0. That is, the height of any student is not in this class interval. Similarly, we also assume that after the class interval 160 to 170, there is an imaginary interval of 170 to 180 and its frequency is 0. We will mark their midpoints. Now, we will connect all midpoints with the line segment. This gives us figure OPQRSTU made of line segments. On careful observation, you will come to know that this shape is a polygon whose vertices represent the corresponding frequencies of class intervals. Since the frequencies of class intervals are represented as vertices of polygon, we call it a frequency polygon. Here you can see that the triangle located outside the line graph can be arranged inside the line graph in this way. This shows that the area of frequency polygon is equal to the area of histogram. In this way, the class interval of 0 frequency helps us to equalize the area of frequency polygon equal to the area of histogram. Now you know about histogram and frequency polygons. Can you tell the difference between the two? Think. Let us tell you. Data is represented in the histogram as rectangles, while the data in frequency polygon is represented using a line graph. In the context of the histogram, we can say that the height of different points of a class interval is fixed. This shows that a class interval in the histogram has uniform distribution of frequencies. If we talk about frequency polygons, then you can see that the height of different points in a class interval is not fixed, which means that frequency polygon do not have uniform distribution of frequencies. In this way, with the help of frequency polygons, we can find an increase or decrease in frequency, that is trend. Similarly, frequency polygons also help in comparing two different figures of similar nature. Now, let's know how to make a frequency polygon without histogram. Here also, we will take the first class interval 110 to 120 before class interval 120 to 130 whose frequency is 0, And similarly, after class interval 160 to 170, we will take class interval 170 to 180, whose frequency is also 0. To make a frequency polygon, we need the middle point called class mark of the class interval. Therefore, we will get the class mark of each class interval. Class mark of class interval is equal to upper limit of class interval plus lower limit of class interval divided by 2. Therefore, class mark of 110 to 120 is 115. Similarly, class mark of class interval 120 to 130 is 125. Similarly, we will find the class marks of all the class intervals. Now, we will draw x-axis and y-axis and represent class marks on x-axis and frequency on y-axis. Taking an appropriate scale on both axes, we will represent different points taking class marks as x-coordinates and its corresponding frequency on y-coordinates. Here, we will represent point O with coordinates 115, 0. Similarly, we will represent other points like this. Now, we will complete the frequency polygon OPQRSTU by connecting all the points with line segments. In this way, we can obtain a frequency polygon even without a histogram. The table below gives the class interval of different widths and their frequencies. Try yourself to represent it in a frequency polygon. So today we learnt about frequency polygon. We will see some interesting examples related to it in the next video. Today we will see examples related to frequency polygon. Nitin started the business of publishing books. Production of books in the first few days of business is as follows. Represent the business progress as a frequency polygon without the help of histogram. We need class marks to create a frequency polygon independently. We know that the midpoint of class interval is called a class mark. Can you tell how we find the class marks? Think. Absolutely right. To find the class mark of a class interval, we divide the sum of upper limit and the lower limit of class interval by 2. Like, class mark of class interval 0 to 6 is 3. Similarly, find the class mark of all the class intervals. Now, we will represent class intervals on x-axis, means days, and frequency on y-axis, means number of books. For this, we have to choose the appropriate scale on each axis. We can take 1 unit is equal to 6 days on the x-axis and 1 unit is equal to 240 books on the y-axis. We will then denote the class mark and their frequency of all the class intervals from the points B 3 and 240, C 9 and 600, D 15 and 960, E 21 and 960, and F 27 and 1080 respectively. After this, we will connect all the points to complete the frequency polygon. We will take an imaginary class interval -6 to 0 before class interval 0 to 6, for which we will extend the x-axis in negative direction. And the class mark of this class interval will be -3. Since books have not been produced in this imaginary class interval, the frequency of this class interval can be taken as 0. Now, we will represent point P on the coordinates -3, 0 and connect point P with point B by line segment. This line segment intersects the y-axis at a point, which we will call point A. Similarly, suppose that even after the class interval 24 to 30, The class interval with zero frequency is 30 to 36, whose class mark is 33, which we will represent as g of 33 and 0 on x-axis. Now, we will connect point F and point G by line segment. Sometimes, imaginary class intervals do not exist, as the number of days here cannot be less than 0. Therefore, the class interval -6 to 0 does not exist. In such cases, we extend only that much part of line segment which is on the right of the y-axis, like here, we will draw AB and ignore PA. Then, we will connect y-axis and intersection point of this line segment to origin O. Like here, we connect A with O. In this way, we get frequency polygon OABCDEFG. By looking at this frequency polygon, we can get various information like the production of books increased till the 15th day, then remained steady till 21st day, then increased till 27th day and then decreased. Can you find out what rate the production of books increased from 7th day to 15th day? Do discuss it with your friends and find out the answer. So today we saw an example related to frequency polygons. In the next video, we will see another interesting example. Today we will see an interesting example related to frequency polygon. Regular checkup is done for the health of the employees working in a medicine factory. A doctor was called to the factory to get the employees' health checked. The doctor divided the staff into two age groups before examining the employees aged 25 to 40 and employees aged between 40 to 60. After this, doctor examined the blood pressure of all employees and made the report shown. Draw the frequency polygon for the blood pressure of both age groups on the same graph. Pause the video and try yourself first. Let me tell you, here we have to show both age groups in the same graph. For our convenience, we will draw a frequency polygon without drawing a histogram. First, we will find the class mark, that is, the middle point of each class interval. For this, we will divide the sum of the upper limit and lower limit of each class interval by 2. Like the midpoint of class interval 90 to 100 is 95. In the same way, we will find the class marks of all class intervals. Now, before taking class interval 90 to 100, we will take class interval 80 to 90 with frequency 0, whose class mark is 85. Similarly, we will take class interval 180 to 190 with frequency 0, whose class mark is 185 after class interval 170 to 180. In this way, the class mark is from 85 to 185. Therefore, we will represent class marks on x-axis, which represent blood pressures, taking 1 unit is equal to 10 mm of Hg. Since here start point is 85, therefore we will not represent class mark from 0 to 85, which we will represent by a kink mark. If we observe the number of employees in age group 25 to 40 and age group 40 to 60, then here to represent the frequency of class intervals, we will take 1 unit is equal to 6 workers, because many numbers are multiple of 6 and other numbers can also be easily represented by this scale. Like 15 can be represented as 2 unit plus 1 by 2 unit, means represented as 2.5 units. Therefore, on the y-axis, we will take scale 1 unit is equal to 6 workers. Now, we will draw a frequency polygon to represent the number of workers in the age group of 25 to 40. For this, we will consider class mark as x coordinates and number of workers as y coordinates. In this way, we will represent number of workers in age 25 to 40 respectively as given. We will connect all this with continuous line segments, which gives us frequency polygon ABCD EFGHIJK, which represents the number of workers in age group 25 to 40 and their blood pressures. To represent that, this polygon is made up of continuous line segments, which represents the number of workers in the age group of 25 to 40. We will write symbol like this. Now, we will draw the frequency polygon to represent the number of workers in the age group of 40 to 60 years. The class marks and the frequency of imaginary class intervals are the same in both cases, so their coordinates will be same in both cases. Hence, the first point will be A, 85, 0, and the last point K, 185, 0 in both the cases. In this way, different points to denote the number of employees between the ages of 40 and 60 respectively will be as follows. We will connect all the points with dotted line segments, which gives us the frequency polygon A PQRSTUV WXK, which will denote the number of employees aged 40 to 60 and their blood pressure. To show that a polygon made with dotted line segments represents the number of employees between 40 and 60 years of age, we would write the sign as follows. Can you get any information from this graph? Think. Let me tell you, we can get various information from this graph. For example, if we look at the vertical line of blood pressure 95, then it is known that those employees whose blood pressure is 95 mmHg are lower in age group of 25 to 40 as compared to those in age group of 40 to 60. We can also see that in both age groups, maximum number of workers have blood pressure as 135 mmHg. Here we see that point S and point G are on the same horizontal line, which means that the number of workers in age group 40 to 60 with 125 mmHg blood pressure is equal to the number of employees in age group 25 to 40 with blood pressure 145 mmHg. Now, find the answers to the following questions yourself. Compare the number of employees of both age groups whose blood pressure is 105. How many such employees between the ages of 25 and 40 have blood pressure of 125? So today we saw another interesting example related to frequency polygon. Today we will learn about mean, measure of central tendency. To represent a group of numbers, many times we need an appropriate number that represents a group of observations. Such a number is called the central tendency of the group. We use different types of central tendency to interpret different types of data, such as mean, median, and mode. In this video, we will discuss the mean. We usually know the mean by the name of average. It is also called arithmetic mean. The mean of observation of a group is the number obtained by dividing the sum of all observation by the number of observations. For example, the mean of given data is 22. We represent mean as x bar and read it as x bar. If we are given n observations like this, then their mean can be written as. For our convenience, we can represent the sum of observations in this way, where Greek letter sigma denotes summation, xi is a variable where I is any natural number from 1 to n. We read it as summation of xi where I ranges from 1 to n. Here n represents the number of observations. With its help, we can now represent the mean in this way. We use this formula to obtain the mean of the data. Now consider that in observations, frequency of x1 is f1, x2 is f2, x3 is f3, similarly xn is fn. Then we can get the sum of all observations in this way and the number of all observations in this way. Remember that here n represents the total number of observations. In this way, now the mean of these observations can be written in this way. With the help of this formula, we can find the mean for given ungrouped frequency distribution. Now, let's understand some characteristics of the mean. For example, here are the heights of some children. To understand what their average height is, we have to find the mean of all children's height. The mean is the only measure of central tendency that takes into account the total value of the data. Therefore, if we require a scale showing the reflection of the total value, in that case, the mean would be a suitable measure. Similarly, if we have to compare the performance of two batsmen, then it will be more useful to compare them by finding the mean of their runs. Here are some observations. Their mean is 20. If we change the observation 29 and write 7, then with the new observation, mean is 18. In this way, the mean depends on all observations. If there is a change in an observation, then the mean also changes. Suppose in a year, 3 districts of a state receives rainfall of 3 cm, 8 cm, 9 cm, due to which those districts had to face drought. And in 4th district, the rainfall was 380 cm, due to which the districts faces flood. If we find the average rainfall in 4 districts, it will be 100 cm. Looking at this, would it be correct to say that there has been good rainfall in 4 districts? No, it would be wrong to say. The extreme value here is 380 cm, which is much larger than the other observations. It has the most effect on the mean. Similarly, peak values have greater effect on the mean. By observing observations here and their mean, it can also be said that if the peak value in observations is too large or too small, then the mean does not represent the best of observations. In situations when the peak value is too large or small, median and mode helps us, which we will read about in subsequent videos. So today we learnt about mean as the measure of central tendency. In the next video, we will learn about another measure of central tendency, that is median. Today we will learn about the median, a measure of central tendency. In the previous video, we saw that we get the mean by dividing the sum of observation by number of observation. Like the mean, the median is also a measure of central tendency. After arranging the data in ascending order or descending order, the middle observation is the median of these data. If we are given n observations, then we arrange them in ascending or descending order. If n is an odd number, then in these observations, n plus 1 divided by 2 will give you the position of the median in the observations. But if n is an even number, then median is the mean of n divided by 2th and n divided by 2 plus 1th observation. For example, suppose one day's rent of living in different hotels in a city is in rupees like this. Let's arrange them in ascending order. Here, the number of observations is 9, which is an odd number. So, the median of these data arranged in ascending order will be 9 plus 1 divided by 2, that is 5th observation, that is 500. Suppose a new hotel started in the same city whose one day stay is 800 rupees. Now, we can arrange all numbers in ascending order in this way. In this case, the number of observations will be 10, which is an even number. In this case, we get mean of 10 divided by 2, that is 5th, and 10 divided by 2 plus 1, that is 6th observation, which will be 525. The median is a middle number, so it divides the data into two equal parts. One half consists of observations whose values are equal to or less than the median, and other half consists of observations whose values are equal to or greater than the median. Now, let's understand some characteristics of the median. Look at these two groups of data. The mean of the first group will be 16, which is a best representative value. Except for one observation in the second group, all observations are similar to the observations of the first group, but that one observation is much larger than the other observations. In this case, the mean would be 27, which cannot be called a good representative value. But here, the median of the data in both groups is 16. Since the values of most observations in each group are around 16, we can say that in both cases, 16 is the best representative value. In this way, when the peak values in the data are too large or too small, the median is a better choice than the mean. At the same time, by looking at the two groups, we also find that if there is a change in the peak value, it does not affect the median. This means that median is not more sensitive to peak values. The median does not take into account the exact values of the data. In this way, it does not use the complete information given in the data. The mean helps in statistics calculation, but the median does not help in this. For this reason, the use of median is limited. So, today we learned about median, a measure of central tendency. In the next video, we will learn about another measure of central tendency, that is mode. Today we will learn about the mode, a measure of central tendency. Mode word is taken from French word la mode, which means trend or fashion. In terms of data, mode is the value that is most prevalent. Like if we talk about these observations, then here 12 is the most frequent. In this way, we can say that 12 is most prevalent among this group of observations. That is, 12 is the mode of these observations. Now look here. Here, the marks obtained by the children in a competitive examination are given. There are a large number of observations here, so it will not be easy to find the mode by looking at the numbers. For convenience, we can arrange the data in a frequency distribution table in which we write the number and show it by its tally marks and the number of times it has appeared in all observations. The count of tally marks tells us the frequency of that number in observations. Can we identify a mode based on frequency? Think. Absolutely right. The frequency of an observation tells us how many times the observation has occurred in all the observations. So, the observation that has the highest frequency will be the most frequent in the observation group, that is, the most prevalent. Therefore, observations with maximum frequency can be called mode. As here 35 observations have come at most 10 times, so it is mode. Here, mode 35 tells us that the maximum number of children have scored 35 marks. Suppose there were 6 more children who got 32 marks. Then, in this case, the number of children who got 32 marks would be 10, which would be equal to the number of children scoring 35 marks. In this way, there would be 2 observations in the group that had the same frequency and the highest. In this case, we would have received 2 modes. Hence, modes can be more than one. Now, let's understand the characteristics of mode. The mode is not affected by peak values of the data. Look at these 2 groups of data. Here, in the second group, the peak value is 698, which is extremely large, the remaining numbers being the same. If we find the mean of each group, we see that due to extreme value 698 in the other group, the changes are taking place in the mean. If we find the mode of these 2 groups, then it is 22.4. You can see that mode is more suitable here than the mean to represent the central tendency. The mode can be used for both quantitative and qualitative data. We have seen examples of quantitative data. Let's look at the example of qualitative data. Suppose a family wants to buy a car. Following are the opinions of the family members regarding the color of the car. Their mode is black color. So, with the help of mode, here will help in making decisions related to color of the car. There are some collections of data in which all observations are repeated the same way, or there are 2 or more modes in the data. In such a situation, the mode is not useful measurement. For example, if the colors of the car were selected by the members of the house in the following way, would it help us to make decisions related to color of the car? Think. Here each color is repeated twice, so choosing one color will not be easy. The mode is commonly used by the ready-made garment industry and shoe industry. Mode helps them to decide which size or measurement should be produced in greater numbers. So, today we learnt about mode, a measure of central tendency. In the next video, we will see some interesting examples on the central tendency of data, mean, median, and mode. Today we will see examples on measures of central tendency, mean, median, and mode. The government organized a free medical checkup camp in a village. The blood sugar level of diabetic patients during the examination is shown below. Find the mean of the data presented. Here, we are given observations and their frequency. So, we should use this formula to get mean. Here, x bar is mean, xi is observations, fi is frequencies, and n is the number of entries in the table. Here, n is equal to 5. Here, we will make the table like this, where in first column, we will represent xi means observations, in second column fi means frequency, and in third column, we will represent multiplication of observation and frequency means fi/xi. Here, the sum of the frequency of observations is 30, which means that a total of 30 diabetes patients were tested for blood sugar level. Now, for each observation, we will find fi/xi means fi multiplied by xi. For first observation, f1x1 is equal to 125 multiplied by 5 is equal to 625. Similarly, we will find fi multiplied by xi for other observations. We will find sum of fi/xi where I ranges from 1 to 5, which will be 4674. In this way, mean is equal to 155.8. Next example, the figures in the given data has been arranged in ascending order. If the median of these figures is 56, then find the value of x. The total number of observations in the data shown is 8. The number 8 is an even number. We know that if number of observation n is an even number, then median is mean of n by 2th and n by 2 plus 1th. Therefore, here the mean of 4th and 5th observation is the median. Here, the 4th observation is x plus 3 and the 5th is 2x minus 11. Therefore, median is equal to x plus 3 plus twice x minus 11 divided by 2. From the question, it is known that median is 56. Therefore, we can write this as, simplify this as, we get a value of x as 40. Next example, 11 students of a class participated in the Science Olympiad of 200 marks. The marks obtained by these 11 students are as follows. So, can you tell which measure of central tendency would represent these figures well? A measure that represents the entire set of data with a single value is called a measure of central tendency. We know about mean, median, and mode are measurements of central tendency. To find the representative value of data shown, we will find the value of each measure of central tendency. Here, mean is 84.09. Now, to find the median, we will arrange the data in ascending order in this way. The total number of observations here is 11, that is odd number. Therefore, median is 6th observation, which is 73. Each observation occurs only once in the group of data shown. Therefore, each observation of group of data is mode. Now, if we compare the three measurements, we see that most of the students have less than 84 marks. Therefore, no approximate estimation of students' marks is obtained from the number 84.09. This is because the numbers 52 and 175 are the extreme values here. The difference between some statistics in the group of data is very large. Therefore, the mean is not a perfect representation of this set of statistics, and the mode of this set of data has no definite value. Therefore, the mode is also not a perfect representation of this group of data. Now, if we talk about the median, the value of median is 73. Here, the number 73 is more effectively representing the marks obtained by the students, and the extreme value of 175 is not having much effect. Hence, median 73 is the best representation of this group. So today we have seen examples of central tendency measurements, mean, median, and mode.